on how to solve these problems. One thing I want to caution you on, for those of you that don't like to write your work, that's not a good idea. Okay? One piece of advice that I'm going to give you is write down everything that they give you, even if you think it's repetitive. And the reason why is, for those of you that will be sitting for the AP exam, sometimes they're like free points. And what I mean by that is, if they tell you what a specific rate is, they want to see that you have been able to pull that out of the problem. You write it down, that it's worth a point. Take all the points you can get for an FRQ. Okay, so that's just some advice. And when we start grading some of these tests, because now we're getting to a point where you guys can answer these as FRQs, we're going to be looking for that stuff. So we are going to be grading for it. Okay, so some strategies for solving related rates problems. Our first step is basically, obviously you read through the problem, and we want to assign letters to all quantities that vary with time. Okay? And we're also going to be giving any others that are relevant their given quantities. So you need to define everything that's in the problem. And it'll make more sense when we start doing these problems. In step number 2, you will identify the rates of change that are known and the rate of change that is to be found. Okay, and we're going to talk about interpreting each rate as a derivative. So whenever you see the word rate, it's the derivative. Because the derivative is basically the slope, right? And the slope is a rate of change. So whenever you see a rate or increasing at a rate of or things like that, you need to look for some keywords. Those are all going to be derivatives. In the third step, you're going to find an equation that relates the variables whose rates of change were identified. Okay, and sometimes you're going to have to draw a figure for this. So up on the board, I have 5 common formulas. It's a good idea, not right now, but you can take Post-its out of the supply boxes, write these formulas on a Post-it, otherwise you're going to be looking them up. They're not in your homework problems or in the problems in a note packet, but on a test or on the midterm or I don't know, the AP exam, everything's embedded in the problem. So it'll give you the volume formula for a sphere or whatever. Okay, but a lot of times in the book they don't give it to you because it's actually in the front of the book, all those formulas. But if you want to take a Post-it from one of the supply boxes, write those down. I will leave them up there for the test. Okay? So just kind of keep that in mind. In the fourth step, once you've identified the formula that you're going to use, you want to differentiate both sides. Okay? And you'll see that it's going to produce a relationship between the known rates of change and the unknown rate of change. And once you have finished, you're going to substitute in all the known values, okay, and then solve for what you're looking for. So one of the most common mistakes that is made is that people will take a look at what numerical values are given and substitute the numerical values in there. But once you substitute in all the numbers, what's the derivative of a number? 0. So if you look at some of these formulas here, volume is equal to 4/3 pi r cubed. If it gives you the radius and you take the derivative of that whole thing, well, the volume's 0. So that kind of makes the problem pointless. So you need to wait. So do not substitute in numerical values before performing differentiation. There is one exception. Unless the number remains constant over time. And we have a problem in here that we're going to talk about. That actually applies that. So if the number is going to remain constant over time, then you can plug it in. Otherwise, you have to wait until after you've taken the derivative. Okay, so far we have taken the derivative with respect to x. So if we have a linear equation, y equals 2x plus 1, and we took the derivative, we would have dy dx is equal to 2, because then it was dx dx, and that canceled out. So now, when we have these related rates problems, we are going to be differentiating with respect to time. So that means every variable that we take the derivative of, it is with respect to time. So if I take the derivative of x with respect to time, it's dx dt. The derivative of y with respect to time, dy dt. The derivative of area with respect to time, dA dt. Volume, dV dt. Height, dH dt. Radius, dr dt. Diameter, dd dt. I think I covered them all. Okay, so everything will be taken with respect to time in terms of the derivative. Okay, so this is going to be a little bit different. So this is just a very basic equation here. You're given a linear equation, and given that dx dt, meaning the rate that x is changing with respect to time, is 1, we want to find dy dt when x is 2. So the first thing we need to do is find the derivative with respect to time of the given equation. So that means the derivative of x with respect to time is dx dt plus the derivative of 4y is 4 dy dt, and the derivative of 3 is 0. Okay, before I continue, does everyone see where the derivative came from? How I got it? Okay, so in A, we want to use this general equation right here. Given that dx dt is 1, so we can make a substitution, we want to find dy dt. Is there any place for me to substitute x equals 2 in? No. Okay, it's not pointless, but it's just the equation that we were given in the beginning. The x goes away when we take the derivative, right? It's not a big deal. It's just extraneous information. We can't plug it in anywhere. It's fine. So we're going to plug in 1. 1 plus 4 dy dt is equal to 0. If I want to solve for dy dt, what's my next step? Okay, fine. Subtract 1. So here we've got 4 dy dt is equal to negative 1. Solve for dy dt. Negative 1/4. Okay? No big deal, right? Just like any equation you're solving for a variable. Using our same equation and derivative, given that dy dt is 4, we want to find dx dt when x is 3. Again, can I do anything with x? No, in this case I cannot. So we're going to plug in what we know, and we're still using this derivative. So dx dt is equal, not equal to, plus 4 times 4 is equal to 0. What's dx dt? Negative 16. Okay, with respect to deriving, with respect to time, does anyone have any questions?
Yes. Why is it 4 times 4?
Because they gave you dy dt. So the derivative of 4y was 4 dy dt. In B, they gave us dy dt. In A, they gave us dx dt's value.
Okay. I get it.
You good?
Yes.
Okay. So we're going to start these problems with something simple, just a circular question. Here it says a stone is dropped into a still pond that sends out a circular ripple whose radius increases at a rate of 2 feet per second. Okay, so here it says the radius increases at a constant rate of 2 feet per second. So this is the rate of change of the radius with respect to time. How would I write that in notation? Yes? That's right. dr dt is equal to 2 feet per second. Okay, so what you're going to notice as I do these problems, I am writing the units every single time. And the reason why is because when you answer these problems, these are word problems. These are real life problems. So you need to answer with your units of measurement. If you do not include your units of measurement, I want to know 48 what? Bunny rabbits? Like, what are you talking about? You need to tell me, and you need to be specific. Okay, does everybody understand what I said? Like, you will lose points if you do not have the rates on here. Okay, so here we have the radius increases at a constant rate of 2 feet per second. How rapidly? So what does that indicate that we're going to be looking for? Are we looking for a rate? No. Okay. How rapidly is the area enclosed by the ripple increasing? Are we looking for a rate? No? Okay, let me ask you a question. The radius increases at 2 feet per second. Can you get an idea of what's happening? If I drop this stone in, here's the first circle, second circle, right? You can get a picture of what's going on. Okay, so that is a rate of change. How quickly something is growing. how rapidly something is growing. These are all key words for a rate. So let me ask you again. How rapidly is the area increasing? Are we looking for a rate?
Yes.
More specifically, for what? For the area. Okay, so we're looking at how quickly the area is changing with respect to time. Okay, so this right here, okay, is indicating that we want a rate. So if you see how rapidly, how quickly, okay, something is increasing, okay, we want the rate, or dA dt, for this problem. Okay, so now we need to see, what are we using, what do we need? So we know we're dealing with area, more specifically area of a circle, because it says a circular ripple. So the area of a circle on the board is pi r squared. True? Okay. So we're dealing with a radius. So I have dr dt, which we'll deal with in just a second. dA dt is what I want. I have one more variable here. What is it? No, not time. Look here. I have one more variable. We already have something for the area. What else is there? My radius. Do I have my radius here at all? Like right in front of me. It says the radius is equal to? No, this is the rate at which it's changing. This is not the radius. So if your radius is changing at 2 feet per second, and they want to know how rapidly the area is changing at the end of 12 seconds, should you be able to figure out what your radius is at 12 seconds? Okay, so for those of you who have forgotten how to do this, some of you just see it. If I know for my radius that the radius is changing at 2 feet per second, do you remember this, some of you? They want to know after 12 seconds, what is a radius? So my seconds cancel here, and Ryan was saying to me it's 24 feet. Does everyone see how we got it? Sometimes it's not going to be spelled out for you in the problem, so you have to take a look at, what do I have, and can I use it to find what I need? Okay, this is where a lot of us struggle with the word problems, myself included. All right, so here's our area formula. Because we are looking at what or how this is changing with respect to time, we're going to have to take the derivative, and we're going to do that when you guys come back from lunch. Okay, so we left off, we have to take the derivative of our area formula. So what is the derivative of A with respect to time? dA dt is equal to, can you classify pi for me here? Okay, so it's a coefficient, so I don't take the derivative of that, right? I'm just taking the derivative of r squared with respect to time. So let's just forget about the pi for 1 second. What's the derivative of r squared with respect to time? 2r dr dt. So this would be 2 pi r dr dt. Does everyone see where everything came from? Okay, so dA dt is what we're looking for. R we found, and dr dt they gave us. So are we ready to solve? I think so. So we have dA dt is equal to 2 pi. My r is 24 feet. And the rate at which the radius is changing was given to us as 2 feet per second. So now we just need to multiply and make sure we have the appropriate label. So we have dA dt is equal to 24 times 2 is 48, times 2 is 96. So we have 96 pi. Don't forget that. What about my feet? Feet squared per second. That's your answer. Okay, questions? Everybody's good so far? All right, so let's take a look at this next example. So typically in the first, 3 to 5 words, you're going to have an idea what your formula is going to be. So my advice to you is write it down, and then you can see what you need and make sure you have all your information. So here we have a spherical balloon is inflated so that the volume is increasing at a constant rate of 4 cubic feet per minute. So first of all, we need the formula for the volume of a sphere. So on the board we have volume is equal to 4/3 pi r cubed. Okay? Constant rate, the volume is increasing at a constant rate of 4 cubic feet per minute. What do you think that is? Yes, sir? Yep, dV dt. So they gave us dV dt is equal to 4 cubic feet per minute. They want to know how fast is the diameter of the balloon increasing. So what do they want to know? So they want dd dt, right? dd dt. Yeah, I said it right. dd dt. That's our unknown. When the radius is 2 feet. So they gave us r is equal to 2 feet. Okay. So if I go back to my formula here, my volume is 4/3 pi r cubed, but they want to know about the diameter. So what I need to think about is the relationship of the radius and the diameter. So I need to make a substitution here. First of all, what is the radius to the diameter in terms of measurement? Okay, so d is equal to 2 times r. Okay, or could we think of this as the radius is half the diameter? Aren't these the same thing? Okay, so what I need to do, because the question is asking in terms of the diameter here, I need to make a substitution for r. So looking at our relationship here, are we going to use the top or the bottom? We're going to use the bottom. Okay, we need to make a substitution for r, and we're going to plug in d over 2. So before we even start taking the derivative, we need to get our formula in terms of what we want or what we have. So we're going to make our substitution. V is equal to 4/3 pi, and then we're going to plug in d over 2 and cube it. Okay, so now we're going to simplify just a little bit. V is equal to 4/3 pi. This is d cubed over 8. Okay, so before I take the derivative, whenever you have a formula like this, it is advised that anything that is a numerical value that it can be used as a coefficient should be at the front, all variables at the back. So can I simplify this here? Yeah, so this is going to become d cubed over 2, and I'm going to multiply by 3. So the formula I'm going to use is V is equal to pi over 6 d cubed. Does everyone see where I got that? So I reduce this with this, and then I multiplied, but I brought all this to the front. So now when I take the derivative, really, I'm taking the derivative of my v and my d. The pi over 6 is just a coefficient. Okay, so if we derive this entire equation, what's the derivative of v? dv dt is equal to pi over 6 times, what's the derivative of d cubed? 3d squared. That's right. And this is actually what we want to know. This is our unknown, right? Okay. So essentially what we have, which will reduce this when we start making a substitution, is we have pi over 2 d squared dd dt. Okay, so we need to start plugging things in. The only issue I have here is I have my radius, but I don't have my diameter. What's my diameter? Everyone see where we got 4 feet? So d is equal to 4 feet. Okay, let's plug in what we know, and we can start moving stuff around. So we know that dv dt is 4 cubic feet per minute, and that's equal to, I'm reducing this, pi over 2, okay, d squared. So that means I have 4 feet squared, and then dd dt. And again, my dd dt is my unknown value. I know there are a lot of items here that you can do in your head, but I don't recommend you do a whole lot. You need to show your work. So we have 4 cubic feet per minute is equal to, what happens when I square this? What do I get? 16t squared. Yep, 16 feet squared. Can I reduce the 16 and the 2? So what does that give me? What's 16? Yeah, 8 pi. Okay? So this is 8 pi feet squared dd dt. All right, what's my last step so that I can solve? Divide, or can I multiply by the reciprocal just so we can see what happens? Is it still the same thing? So I've got 1 over 8 pi square feet times 4 cubic feet per minute. This is equal to dd dt. Okay, why was this important? What do you see is going to happen? Yeah, the feet are going to reduce. So this goes, and I'm left with one of these here. So what that leaves me with is 1 over 2 pi feet per minute is equal to dd dt. Okay, questions? You guys okay?